Today I'm going to talk about PyTorch, and I have some assumptions about you guys. So I'm assuming that all of you are familiar with the basic problem that ML is solving. We have nature as a function, and we have to figure out what that function is from some data, some noisy data that we have gotten from some measurements. Essentially, what we need to solve any ML problem is some data, a model that we can fit to the data, a loss function that tells us how accurate we are, and something so that we can improve our loss and optimize it. And PyTorch helps you with all of those. It allows you to build a model, and it allows you to optimize that model. I'm assuming that all of you know what derivatives are, even if it's superficial, and that there are specific rules that have already been established to figure out derivatives for common functions like addition, multiplication, log, stuff like that. And the last one is, I'm hoping that you have a fair idea of what gradient descent is. And now there are some disclaimers. PyTorch is currently 3 million lines of code in C, C++, and Python. And now the next point might come as a surprise to you. I have 20 minutes. And I did not write PyTorch. This is a story of data and functions. And perhaps every single story in data science follows that tale. But let's start with something that I like, or my favorite thing in the world. Let's start with the F word in mathematics. So let's start with functions. What is a function? A function is something that takes data as input and spits out data as output. And now data can be anything. It can be sets, values, other functions, lines, anything. So it's a very malleable concept, very abstract concept. And I guess we have already blurred the line between functions and data at this point because you can see that data can be other functions. So we can have data acting on data or functions acting on other functions. But what can we use these functions for? What is the utility of these functions? Well, we use functions all the time. In every single thing, we are already using some kind of a function. Basic operators like addition, multiplication, division, all of these are functions. Add AB and multiply AB are the most basic functions that you can find in linear algebra and that can define the entire field. And then you have all of these which can be derived from these. But I think that the true power of functions lies in function compositions. That is, you can take a function and augment it by applying another function to it, and what we get out is essentially a function. And here's the thing, I hate equations. I've seen equations, they seem very rigid, monolithic, and I want to break them. And function composition allows me to do that. It allows me to express any equation like ax squared plus b, by plus c. I don't even care what it is about. I don't like it. I don't want to look at it. And it allows me to represent it as something more elegant. Let's say this piece of pseudocode. But it's still not very intuitive, right? Like, what if we have 1 million parameters? How can we see every single composition that goes inside it? So I would like to propose a new schematic. A more intuitive way to see how functions are composing inside our black boxes, and exactly how we can trace a variable through that chain. So this is what I'm proposing. We define a graph where the function is essentially a catalyst. We don't even have an object or a struct for this function. It is just free floating. All we have are nodes which have some values and another node which is also a value. But this directed graph essentially is created by this function being applied to x and y. The beautiful thing about this schematic is that it can extend generally to data in this way. So we have some data, and that can be any abstract data, and you have some other data, and then you get some output data. And now this is the ugly function that we saw earlier, the equation, and this is the trace for that function in our schematic. For now, for ease, let's call this a composition trace, the schematic that we just developed. But some of you might be wondering, why go through all this trouble? Who cares? We have equations. Equations are nice. They don't bother us. Why do we have to change them? Well, because computers solve differentiation, and it becomes a very computationally heavy process when you have nested compositions. For example, differentiation is hard. And other differentiation techniques make it almost impossible to solve deep learning problems where you have, well, now currently you have like billions of parameters, but when auto differentiation was first invented, we had, let's say, 1,000 parameters for every single model. But even at that time, the computational cost was quadratic. So this is not feasible. You cannot use symbolic differentiation because you get equation bloom because it just keeps on expanding. And you can't use numerical differentiation because for every single variable, you have to do 2 passes to figure out what the difference, what the derivative is. Our schematic actually solves this in a very elegant way. It exposes function compositions and allows us to exploit the chain rule. Now, I don't know if all of you guys remember what the chain rule is, but chain rule is something that was taught to us in calculus, and it allows us to see how function compositions can be broken down to create derivatives. So what does it look like? Chain rule looks like this. If you have a function composition h, which is f of g, then the derivative of h is basically the derivative of h is the derivative of f applied to g, the function itself, multiplied by the derivative of g. Why does this matter? Because it's breaking down composition into a linear operator. This right here, the multiplication sign between the two, is a linear operator. So you're taking something that can be a non-linear function, and its derivative is going to be a linear function. Now, why do this? What's the point? Because if you think about deep learning architectures and deep learning models, every single model has multiple layers. And every single layer can be considered to be its own function. The chain rule and the way we have defined our schematic allows us to figure out the partial derivative at each level of this massive computational chain. But how? How does it allow to do that? So do you remember that a few slides ago, we saw these operators? Well, it turns out that we have already defined a very well-defined set of derivatives assigned to each one of these operators. And do you remember that initially we had functions only as catalysts and not really in the schematic itself? We need to change that now. Because what I'm proposing is we add an operator block. In the forward pass, it's going to give you the function that you need. And when you want to go back, it will give you the derivative of that function. So something like f dot backward. If anyone has used PyTorch, you might be able to see where this comes from. In the forward pass, you can have 2 variables, and you can have z, which is f of xy. And in the backward pass, you can have z, which goes back, and you can see that the arrows are highlighted accurately for the function to highlight, and you get the derivative. And this is held by the block itself, by the function block. Now let's bring it all together and see what picture we have formed. We have a schema that we have painstakingly developed to express complicated functions in terms of simple, very simple operator compositions. We have a way to compute partial derivatives using the simple operator block that we just developed. And most importantly, we have the mighty chain rule. This essentially allows us to walk back, literally walk back from the cost function right to the input variables and accrue the gradient. And what we do is we call these partial derivatives adjoints. This is just terminology that comes from the literature, and they can be propagated down. But this is how a forward pass would look like. So you have two variables, and in the forward pass you can go to the next level, get an operator, get an output, add another function, and have a cost. And essentially that's what you want. In the backward pass, you start with the cost, and you take the derivative of the cost with the cost, which is 1. And then you go back further, and then this function is now going to trigger the derivative. The derivative part is the part that's below. So now G prime activates, and it actually gives you the derivative of dc, which is partial derivative of the cost by the variable that was at that level. And then you can go back further, and then you have this function, and now you're supposed to derive this entity dc by dz by the new function f. And that kind of explodes, because at each level we have defined it such that we can have one pass and it will get back to every single input. That is the power of reverse mode automatic differentiation. So if you can see, we have mult blocks here. They are there because of the chain rule, yeah. And these multiplication blocks are essentially going to take the previous gradient, multiply it, and give us our cost with respect to the variables that we began with. Now, if you guys notice something, our adjoint graph also follows our schematic, because we are starting with variables, or we are starting with values with nodes, and we are applying some operators to them, and then we are getting other nodes and other values and stuff like that. So it follows our schematic very closely. Why does that matter? Because then you can overlay these. You can overlay the forward pass and the backward pass, and you can optimize a few things. You can optimize space. You can see that all of these functions are being repeated, so you can get rid of those. And I'm just going to show you how you can get a reverse mode trace for a single variable, let's say x, after these things have taken place. So you have something like this. You have reverse mode, and this schematic accurately describes reverse mode automatic differentiation. But now you might be wondering, hey, I thought this talk was about PyTorch, and you haven't mentioned PyTorch once in the 15 minutes you have been on stage. What is happening? Well, PyTorch implements its functions with something called adjoint computational graphs. And from the official PyTorch documentation, you can kind of see that we have visited this before. We saw a similar structure. On the left, you can see like the forward pass, where you can see x1 and x2 going in and going through a bunch of function blocks and then getting to z. And then you go through the backward pass and you get the derivatives with respect to the cost. So we have seen this. And indeed, we have. Because the schematic that we just developed is that. And that's exactly how we do it. And that is my time. Do you have any questions? None? How much time do I have?
You still have 5 minutes. So anyone have any questions for Soumitra? Here, I'll ask a question. Or
He has a question.
yeah, go ahead.
So PyTorch is more academically oriented because it allows you to create something called. So PyTorch is very Pythonic. So it allows you to create dynamic graphs. So you can change them on the fly. And that's what makes it perfect because you can change your models really quickly. You can make updates to it, and you don't have to compile these models. Other libraries, other frameworks. Which ones did you mention? Keras is basically like a wrapper, but which? Yeah, TensorFlow makes rigid or used to make rigid graphs until recently because then it saw that PyTorch was getting some traction, so they also added some dynamicity in the graphs. But TensorFlow is really good at adding some optimizations, which makes these calculations over graphs really fast. So academia is the answer.
I'll ask one more question.
Sure.
What are some of the use cases that we can use this for?
What do you mean?
Like real world use cases?
Like the computational graphs?
Sure.
So many things. I think most of robotics. So right now there are tons of robotics libraries which are being developed without any kind of structured directives, and computational graphs can come in and they can essentially have like a chain which goes. So imagine that you have a robotic arm. You can have a chain that basically takes you from the joints all the way to the end effector, and that can be expressed beautifully with computational graphs, making it differentiable in the forward pass and the backward pass. So robotics is a field for that. Certainly. Yeah. Okay, that is an excellent question. So, how much time do I have? Okay. So, with GPU architecture, we discussed data, right? We started this thing with data and functions, and I kind of talked about the functions part of it. But GPU architecture, and PyTorch in particular, leverages something called the tensor. And tensor is their main data class for expressing all of the other data classes that they can have. So tensor can be a scalar or an n-dimensional vector or a n-dimensional tensor. And all of the optimizations happen on the tensor side and not on the graph side. So does that make sense? So yeah, so imagine that you have the same variables and they go through a lot of changes. Like basically PyTorch or TensorFlow, all of these libraries kind of keep the space intact and just give you the illusion of change through the chain.
All right. Thank you, Soumitra. Everyone give him another round of applause.